Okay, so what do we have next? At 6:30, so just right now, we will have Bartosz Moczulski, Once Upon a Thread in the Mutex. Right? So Bartosz will tell us more about it. A fun fact about him is that he is interested in medieval calligraphy, and being left-handed, he has to do it upside down. Bartosz is a software engineer with over 20 years of commercial experience. Bartosz is a big fan of Linux ecosystem, and he calls him a Linux detective. He rarely leaves any bug uninvestigated. Right? In his spare time, what might be good for all of us, he's making wine. So warmly welcome for Bartosz. The stage is yours.
This fall, who protects you? Data and Mutex.
Whom do you protect?
Will eventually find
Can this be called here?
their own happy ending.
This is sheer nonsense.
From creator of Shadowstack
I have to end it, once and for all.
and Linux Detective Toolkit,
Two of you belong together.
Bartosz Moczulski returns
I pronounce you
to put a race to an end.
synchronized value.
Once upon a thread in the Mutex, the road to synchronized value and why it matters.
See you at CodeBase.
So let me dedicate this nice round of applause to my beloved wife, who is the lady behind the scenes. Behind every great man, there's a great lady. And she kindly volunteered to be a camera operator on this short film and a set manager. So thank you. That said, multithreading, it's easy. Said no one ever, except maybe a few gifted ones. Yes, and my wife also has this nice t-shirt. She never wears it outside, she only wears it inside. Maybe there's a message there for me, who knows. However, this good advice doesn't apply to multithreading, because in multithreading, we need to apply discipline, not just brains. And let me start with the problem statement, what I want to discuss today. Just look at the code. We've got two variables and two mutexes. And we want answers. We want to know if either of these variables is guarded by any of those mutex. And if so, by which one? And obviously, we want to check whether any of these mutexes guards any of these values. Maybe they guard the other. Maybe they are for a different purpose. Who knows? Just by looking at the code, it's impossible to tell. And we've got a function which uses one of the variables. And it has a comment just before it that you must hold the mutex to call this function. Yep, good luck. So we want to be able to tell which mutexes are held at every single point in our code. That would be lovely, wouldn't it? And we want a fourth property. We want to make sure that whoever calls our functions indeed holds these mutexes that it's required to hold. Yes, make sure that they are held at the call site. And ideally, we want it in C++ syntax, because of course, I mean, we don't want compiler extensions, we don't want custom annotations, we don't want macros, because macros are not kinky. So that's the thing I'm after, that's what I try to solve. And yep, multithreading. The multithreading comes with a multitude of challenges, of course. We've got data races, shared data. If you don't share your data across threads, you don't have the problem, but most often you do. So you've got like no mutex where there should be one. You've got two atomic variables which you think are a single atomic pair, but they are not, in fact. And you call some functions from some libraries, maybe not the standard library, maybe from third-party libraries. And you may not know whether they are empty safe. And with mutex, wherever there's more than one mutex, there's always fun thing that comes with it, which are deadlocks. And it always takes 2 mutexes, at least 2 of them, maybe more, to create a deadlock. And you've got ABBA locking, which is the simplest form of deadlock, and deadlock prevention and detection. I will mention it briefly, but not to a big extent. So why do we care at all? If you don't trust me, you can trust the great old ones of C++. And the very first core guideline is assume your program will be run in a multi-threaded environment. You can check it up online as well. This like the list is very long and very good advice. So, as was already mentioned, I consider myself a Linux detective because most of my professional time I spent investigating bugs in existing code, not writing code of my own. It's not to say that I'm not a programmer. I code sometimes, but more often it's like, oh, there's a code. Yes, there is a code, and there's an error in it. And I investigate it. And you may know that, or may not. I spent like 20 years of my time doing digital TV equipment, set-top boxes, these little things that you connect to your TV on the wall, such that you can enjoy Netflix or terrestrial TV or whatever floats your boat. There's a lot of multi-threading in TV. You can take my word for that. And recently, like not so long ago, maybe last year sometime, I was investigating a crash like this one. We have a thread X, which locks mutex A, and then it locks mutex B. And in the meanwhile, another thread, let's call it Y, locks mutex C, and thread Z locks mutex D. And thread X gets to be executed again and tries to go for C, and it goes in a vicious circle, and that's a deadlock. That's the very definition of a deadlock. From a graph theory perspective, deadlock is just a cyclic graph. So graph theory is a pretty well-known branch of mathematics, and if you know all the nodes and all the edges, you can instantly tell if there's a deadlock or not. That's not all. There's a fourth one, if the victim. And the victim happens to have a watchdog in it. And so when it doesn't get to lock whatever it wants to lock in the time that it expects, the watchdog gets angry and crashes the program, and obviously that's how I got my core dump. So I had to analyze it, and of course, all the threads instantly popped up in the debugger. That was quite easy. However, the challenge was, all right, now I know which mutexes are involved and in which places. Now the great question, which variables do they protect? So I scratched my head about it for a little while and figured out that, actually this thread X doesn't really need the resource B in order to continue. So we can release it temporarily, then go straight for C, and then B. The other thread gets to log B, and everything goes just well, right? No more cycles in the graph. And the watchdog is happy. And right, so let me present you the history of what was possible in C++ in terms of multi-threading. That's how it all began. I mean, that's all. There is no more on this slide. In C++ 98, there was nothing, and the C++ just thought, no, there's this pthread. It's not my problem. And on Windows, you've got the Windows multi-threading API, and it's not of our concern. It didn't last long, luckily. And in C++ 11, a set of multi-threading primitives came along, and the first one was mutex, or more generically, lockables. There are a few kinds of lockables, and mutex is just one type of lockable with extra requirements, but not too many. So we've got unlock and lock. We've got try-lock. That's important for locking multiple mutexes in a deadlock avoidance manner. And we've got try-lock and unit lock. And this one is fun. A mutex and the recursive mutex and the timed mutex are all secretly a pthread mutex, at least on all the Linux platforms that I encountered, both in GCC and in Clang. They all use pthread mutex under the hood. So that's funny. Yes, unfortunately, Mutex and lockable in general, they come with a huge problem. There's a RAII violation in the design. That's how the API looks. Lock, unlock. That's a valid lockable. That's the code I wrote, but it's a valid lockable in terms of C++. So it initializes the mutex, distracts it in a destructor, and there is a lock and unlock. And it's a major food gun. Because if you forget to unlock whatever you've locked and you go straight for destroy, you end up in a problematic situation, to say the least. So yes, the great old ones of C++, they discovered that pretty quickly, and they said, no, please don't use it. Don't use the plain lock, unlock, just go for RAII. And again, not my word, you can check it up. So we've got mutex. We also have locks. Locks are optional RAII wrappers for locking. And unique locks, shared locks, they all share the property that they can be unlocked throughout their life cycle. So you can lock them initially or not lock them. You can defer locking such that it gets created but it remains unlocked. And you can maybe lock it later. You can adopt an existing mutex that already got locked by someone or something else. Locks. And we've got guards. The guards, they're similar to locks, but they differ only in that sense that they mandate unlocking and locking, and you don't get to unlock in between. You lock or adopt in constructor, and then you unlock in destructor, period. It would be lovely. However, mutex is, like already mentioned, that mutex is under the hood is a lock, right? So we've got a semantic problem here. A lock, a shared lock, is not shared in the sense of shared pointer. No. It's a unique in the sense of unique pointer. You cannot copy that around. You can move it around, and each thread locking something in a shared mode gets its own unique copy of a shared lock. Okay, so. Now the next thingy, stud lock. This one is lovely. It's C++ 11, like the first attempt. It's not a lock. It does lock, and it actually requires an extra guard in order to work properly. And luckily, it got replaced with scoped lock in C++ 17. So we do use scoped lock instead. And we've got guards. We've got scope locked, which is a guard, because you cannot unlock a scoped lock in between. So in this sense, it is a guard. If you think it's a little mess, you're not alone. I'm with you. And here you've got a little cheat sheet. You can print it out and hang it somewhere close to your desk so that you always remember what's fishy about C++ multi-threading APIs. And there's deadlocks. I mean, deadlocks are bread and butter of us engineers having to work with multi-threading, isn't it? So little did I know that mutex.lock function can actually throw an error. I would have locked. There's an error. I throw it. Now, have you seen it ever? Please raise your hands. I mean, don't be shy. 1 hand, 2 hands. Okay, not even 3. Fair enough. I didn't know that before preparing this talk. So yes, I would very much like to pay the cost, because of course C++ is about zero-cost abstractions. I want to pay this cost because it will save a lot of engineering time. Yes, I did discover where this error would be thrown, this exception would be thrown, in very simple cases, like the very simplest one. If you lock your unique lock twice, then it will be thrown, and only then. So we have the C++ pyramid. So the C++ comes along and says, yeah, maybe it is my problem after all. And it started in C++ 11, so like a little while ago. And with that, let me go to a demo that I prepared for you. I've got now you've seen it already, right? It's the simplest lockable that does work. You can use this thingy with stud unique lock, stud lock guard, whatever you please. Here's the timed version of it. If I add try lock and try lock for and try lock until, it becomes a valid time lockable. And here's an interesting one, which I will show you in one of the examples. pthread has this type called error checking mutex. Normally, if you just go with the defaults, it will give you so-called fast mutex. But you can make it, turn it into an error checking mutex, which will do some extra checks for you. So that's it. And here I've got, let me start at the top and make sure that, yep, let's start with the first example. What does it do? We are using logguard here. So what does it do? I'm showing that with ltrace. It just creates the mutex, locks, unlocks, destroys. Nothing fancy. A second example, if I use a unique lock instead, it does the same thing. Create, lock, unlock, destroy. Let me scroll it up. And if I now use a deferred unique lock with a lockguard that follows, yes, it's still the same thing. Lock, unlock, destroy. Now, if I create a unique lock which is deferred, and then I create a unique lock that logs that deferred unique lock, yes, you can do it. Interesting. Guess what happens? Nothing changes. And obviously, you can return a lock from a helper function. Yeah, so here we've got all the same thingy, and it also works with std_mutex, because why not? I mean, obviously. Yeah, std_mutex is slightly optimized because it initializes mutex with a static macro that pthread offers. So, and then it's smart because it knows that, hey, actually, the pthread mutex destroys an empty function, so I can just get rid of it. Now we are proceeding into a more interesting land of locking two things together. And we've got the C++ 11 thingy, std_lock, with lockguards, like it used to be, number 7. And of course, it initializes two mutexes, locks the first one, and try-locks, that's the difference. Try-locks the second one. And it succeeds, so yeah, obviously it continues merrily. And yeah, you can do the same. No surprises with scoped lock. You don't get to write all this extra code here. You just use a single function and it does what it should have done from the start. And it's great. If you are blessed with C++ 17 and onwards in your company or on your project, just use that. Now when we want to... Okay, this one is pretty self-explanatory, but let me underline the important highlights. Locking. There's this myth, maybe no, not myth, like a unconfirmed notion floating in the air that if you want deadlock avoidance, you have to lock your mutexes in the order of the increasing address. That's not true. And please have a look. I start with muting first, then second, and then in the next line I lock second, then first. Let's inspect the addresses. It starts with 60, then follows on to 90. And there's a second pair, 90 to 60. So it's not true that it has to be in the increasing order of addresses. As a matter of fact, I've got a better example here, which shows how these things would be locked. If the third one, we will lock 3 mutexes right now, if the third one happens to be locked already, and I need to increase this console. So the thing is here, we've got 3 mutexes, the third one is locked, and we try to scope, there we go, well, no, not here, scope lock all 3 of them in the foreground thread. And that's number 10. So, there you go, it's a lot, isn't it? So what happens, I mean, the third one is obviously locked already. So we try to lock the first, it succeeds. We try lock, sorry, okay, I'll come in again. We fully lock the first one, we try lock the second, we try lock the third, and it fails. So then we get to, we need to unroll everything, what we've already locked, and start over. And we start from the first one again and continue to second and third. And we keep hammering all 3 of them until the end of days. This is obviously not very efficient. That's why it changed in GCC 12. My default example were compiled with GCC 11. If I switch to 12, you can see that, okay, that's changed. Same code. So we try lock, the second try lock phase, I mean the third mutex is still locked. We unroll, and then we proceed to fully locking the third one. They change into a round robin. So depending, I want this to soak in. Depending on your library, the deadlock avoidance algorithm may be different and may be better optimized. And that's the takeaway of putting the effort into upgrading your toolchain in your project. If your boss needs some argument, oh wow, should we do it? Everything keeps working. Yeah, but can work better. So that's it. Moving forward to an interesting case. Let's stick with 12. Why not? The error checking mutex. If you unlock it from a different thread, then you locked it. Then it reports an error and says, no, you must not do that. You should unlock it from the thread that locked it. So that's the result from paying the extra cost of the check in the error checking mutex. And if you do the same in the standard mutex, nope, it's happy. Sorry. Lock. Right, because I need to show all the threads here. So you can see here we've got, where was it? I'm not quite sure what happened here. So in a nutshell, stud mutex allows you to do it and wouldn't be bothered at all. And if you happen to make a mistake and try to lock two things, I mean the same thing twice, you get it, right? It will keep trying to lock until the end of days. Coming back to the slides, because obviously that's not a situation we want to continue. So we move to the present. And let's have a look at the class. Does it look empty, safe for you? Yes? No? Anything? Okay, it doesn't show anything that would be empty, safe. It just, okay, a single value and two methods within it. No locks, no nothing. So maybe we'll sprinkle some mutex around and some locks as necessary. That's better already. Now let's refactor this class a little bit and maybe introduce the public interface, which will be locked, and the private helper methods, which will no longer need to be locked because the public API will take care of that. Oopsie. Down in the bottom, we forgot to lock. But the code compiles, so it's still empty, unsafe. So the last one, we introduced a second member and a second mutex. And we still lock it properly, right? We lock M1 before accessing foo, and we lock M2 before accessing bar. So the question remains, how do we know whether we locked the proper one? There are two of them. Which one is for which member? We don't know that. So the challenges, and let me reiterate on the slide that I showed in the beginning. We want to be able to express data to mutex relationship. We want to to make sure that locks are indeed locked, our mutexes are locked whenever we access the data that these mutex guards. And if possible, we want it in C++. And yes, it's kind of doable even today. Have you heard of thread safety analysis? One hand, two, three. Okay, not fourth. Okay, cool. So I'm glad that I'm bringing up this topic. The thread safety analysis is an extension available in Clang and has been for several versions back. I think I started with Clang, I don't know, 13, maybe 17, and it was already there. Don't quote me, please. But I think 17 was already available. So thread safety analysis is a set of extensions by the compiler, which come in the form of annotations wrapped in a nice macros, such that you can enable or disable it depending on the compiler that you use. So the first one is guarded by, and if you have a variable that is protected by certain mutex, you can express it in the code. You just add this guarded by annotation, and now the compiler knows which mutex should be locked in order to access this variable. The other one is requires. And if you have a function which touches the variable, okay, right now the compiler will stop you. It would say, no, you need to lock it first. But you can tell, yes, but I don't want to lock it myself. I want the caller of me to lock it instead. Requires M. It means the caller must already be holding M provably. So that's way safer. And there's a mild form of deadlock prevention. If you have two mutexes, you can tell the compiler in what order you expect them to be locked. So acquired after and acquired before, obviously, for symmetry. There are a couple of pros and cons of that approach. The pros are obvious, right? You get to express which mutex holds which, protects which data, and vice versa, and locking is forced. However, on the cons side, it only works in Clang. It used to work in GCC, supposedly, but it's been removed, and it's only remained in Clang, and the development continues only there. You require some annotations, so you need to change the code. Wow, sorry. And yes, only libc++, so not the GNU version, but the Clang version of C++ library. Not sure about Microsoft, haven't checked, I admit. And notably, unique lock doesn't work with that, for reasons I will mention in a second. So looking at our pyramid, Clang adds TSA, and that's interesting. And I will just show you the code, which does work. Switch to demo 2, and let me start with these annotations. So these are the annotations. You can get them from the documentation page. I think I'm a few versions behind because there's more of them now, but this is like a good enough subset, and it expands to the attribute, like a classic attribute, obviously compiler specific. So if we look at the code right now, something similar, account, and you transfer the money back and forth, and you've got an account which has an owner and which has some balance. And if you are working in a bank, please don't implement the banking system like that. That's just for the example purposes. So I add here the guarded by, and I tell that, okay, balance is protected by mutex lowercase m, and owner name is protected by mutex capital M. And what now? Yeah, and I can just run. I mean, it obviously compiles and runs. All right, so account TSA to dumb. Why? And John Doe has $1 million, and he comes over to the bank and deposits another 1,000, and he gets a bonus of $10 for that. And in total, he gets $1 million and 1,010. Let's look at the code, though. We've got a deposit locked function. It's a private one, and it requires a mutex. Let me remove this annotation, save it, and rebuild it. And I'm rebuilding it in a couple of flavors, so using GCC, using Clang without the TSAN annotations, without TSA and with ThreadSanitizer, and finally with thread safety annotations. And all the first three, they compile just fine. And the fourth one, with TSA enable, it says, whoa, you must not touch the balance because you haven't locked the proper mutex. So this won't work. And that's great, right? Because you get the error early, not at runtime, not if your customer sends you over a bug report or whatever, or maybe something goes unnoticed and certain hackers get your dollars from your account to their account. You know, things happen. So that's one thing. The other thing, if we, just checking my demo so that you don't miss anything. Revert and comment logs, of course, yes. If I go to the function being called here and comment out the logs and rebuild, it comes up with a different error saying, okay, you must not call this function here because you haven't logged, right? The thing I mentioned about unique lock, it doesn't work. And it doesn't work, or maybe I've got a better example somewhere further down. Do I? I should have. Yeah, I've got it here. Let's have a look at this example. Why unique lock doesn't work and cannot work. Yeah. First of all, let's try to build it with a unique lock instead, and it obviously will fail. Let me make the code larger. And unique lock cannot work for this very reason, because it can get unlocked in some conditional flow throughout your instructions. And over here I've got a random, if it's even, then unlock. But in reality it can be some other function called being called somewhere else, passing back and forth the mutex. So maybe about this, no, okay, about this already it wouldn't be able to reason. With a unique lock, you don't know whether it's locked or not. So let's stick to the lock guard instead, which is always provably locked. Okay, still working? Very cool. So I've got a thing that tries to lock. Let me unlock the code, uncomment the code, and this looks like the other method. The only difference is that it tries to lock the mutexes in a different order. And all three compilers like, okay, that's fair enough, you do whatever you please. However, with TSA annotations, you get an error, and it's good that you get an error, because please have a look what happens when I try to run it. TSA with, sorry, not with TSA, with ThreadSanitizer. Okay, ThreadSanitizer caught that error at runtime. That's way too late, right? Usually way too late. And it's not too late and if you haven't rolled into production, but it's kind of late. It could have been caught at compile time. So it looks okay. You are locking two mutexes and you establish the order during the first call, and then you call it from somewhere else, and then you try to lock it in different order. And that's the very definition of ABBA. Because right now it's sequential code, but maybe it will be called from another thread later on, somewhere in your program. So that's a warning that you get. And obviously you can use Valgrind. Where's Valgrind? There we go. So if you compile it entirely without TSA, without nothing, and you run it in Valgrind, so vanilla code, it will come up with somewhat similar, although maybe a little longer explanation, saying essentially, okay, you've locked it in a certain order, and then you're trying to lock it in a different order. That's the thingy. Yep, and unique lock failing with an error. Yep, already showed you. So that's the current state of affairs. That's what you can use even today, if you so wish. And obviously you can apply all those annotations to your own lockable construct. So it doesn't need to be Stud Mutex, it doesn't need to be it can be your pthread mutex wrapper or something entirely different that you happen to be using. Now, the future, because so far I've been talking for give or take half an hour and I haven't told you anything about the synchronized value, which is the subject of our talk. The synchronized value, first of all, who heard about it before my talk or before learning about it? One hand. Not too many, that's great. Okay, two, three. So a couple of you. It's a proposal for C++ library raised by Anthony Williams, the man who knows about multithreading a lot. Not sure if everything, but certainly a lot. And the proposal goes like that. Let's introduce a class to our C++ library, which will contain two members, the data and the mutex. Just that. All of them private. You don't get to access any of those, neither the data nor the mutex. And alongside, there is an apply function, similar to stud apply that you can use today for tuple access. So to this apply, it's like a special overload, which you pass a lambda or any other callable, and you pass a set of synchronized value variables. So like this pairs of data in mutex. And that's how you get to access your data. So assuming you've got this balance variable over here, which is a synchronized value, you call apply. At the end, you tell it, okay, apply it to the balance. So essentially lock the balance and provide it into the lambda or whatever other callable you desire. And inside, this callable will take a reference to the data inside the synchronized value. That's the only way you can access the data inside. And when you get to access that, you have the guarantee that it is locked and safe, and you can modify it as much as you wish. So there's another example if you want to synchronize two variables, because when you're sending money from account to account, you want to synchronize both of them, because otherwise you know what happens, and you've probably tested that on a couple of times in your terminal. I mean, most of the time it works, but sometimes it doesn't, and you've got like imbalance. So the only thing you need to do, you pass two variables here at the end, and both will be locked, and they will be locked in a deadlock avoidance manner. So just like the one I showed before, depending on your C++ library. It actually does use std scope lock under the hood, or can at least. It's not mandated, but it's the simplest choice. And yes, you take two parameters which both are references to relevant variables, the locked data inside them. All of that certainly works with classes, because we are C++, we talk in classes mainly. So an interesting structure here would be, yes, create a private struct data member, data type, sorry, not data member, and then add a member or synchronized value of that data. You don't create the data itself, you only create the synchronized value of the data type. And if you want to modify it, you can log the data and you get access to the interiors, like on the previous slide, and it also works with within methods. Why wouldn't it? And here comes the most important detail. Look at that. If you happen to have a method anywhere in your code, anywhere in your class or outside of it, which takes the raw data reference, you are absolutely guaranteed by the design of this feature that this data is locked somewhere up the stack. It may be a few stack frames up, maybe just the next frame, doesn't matter, but within this function, there is no other way to access it only through locking. And once it's locked here, you're guaranteed, okay, we are the only one modifying it. We don't need to worry about locking. It has been taken care of. So data plus mutex. The good, I mean, both of these sides will be the benefits. We are explicit. The locking is forced. There is no way to access the data unlocked. And we don't need any compiler extensions, and we don't need some special annotations, attributes, whatnot. It's pure C++. Now, the things that you cannot do, which are also a good thing, you cannot access the data directly. The lockable, the mutex, is hidden away from you, so it's like you don't get to tamper with it, like mutex.unlock because I want something, because I think I know better. No. And you don't get the accessor operators, so you cannot assign anything to the data unless within the apply function. You don't get to dereference it because I just want to read. No, you don't. You want to lock it, then read it. And if you so desire, you can return a copy, but not a reference. And you don't get the arrow operator, which is available in some alternative implementations. And for me, these are all positive sides of things. Click. So we've got this apply. I mean, that's nothing new. That's what I showed on the previous slide. And there's another approach to this topic, which is like returning a handle. Return something that can be the reference, which already represents a locked data. And that's what alternative implementation available in Boost actually does. You use it such that dot synchronize or Boost synchronize, if you want to lock multiple things, returns you a handle which you can dereference, or maybe there's a arrow operator that you can use, and you can just keep on calling the methods on your object. However, it has a drawback, in my opinion, and that's just an opinion. I mean, your mileage may vary. Have a look at the right part of the slide over here. You lock two thingies, and you transfer the amount, like sending the money back and forth. You decrement from one account and send it to other, and add it over there. Look, watch closely as I press the clicker. Done. Have you noticed? Different order. That's ABBA. That's how easily you can create an ABBA lock using this pattern. And you can think you're smarter than that and you will never make a mistake. Trust me, you will. I will. Everybody will. Because look at the next one. If we use it in a class context, if there's a method, just check it out. You first lock this balance, and then you lock the other balance. And if it so happens that I send my money to you, and in the same instance you try to send your money to me, we are in ABBA deadlock over here. Not good. That's why I think the apply with a callback, with a lambda, is superior to the handle approach. However, all of them might work. Oh yeah, so that's that's the best example. With the handle approach, you can think you are synchronized, but you are not synchronized at all. These are four different things, four unsynchronized accesses: read, then write, and again read, then write. There's no synchronization here whatsoever, and it's possible. With the proposed state synchronized value, it wouldn't be possible at all. Except if you really insist on doing it the wrong way, on the right hand of the slide, we're back in the proposed state synchronized land. If you really insist on making two subsequent applies, then yes, it's still a BBA. But would you? I mean, this one is way easier. Just add another parameter over there. And the worst thing you can do with synchronized value is to return the reference or a pointer to the data being protected. You can do it if you so desire, then you're on your own. You simply let go of any synchronization and any help whatsoever. So, I mean, yes, and core guidelines, back to core guidelines. It's not even in the standard yet, but it already made it to C++ code guideline. CP stands for concurrency and parallelism. So CP.50 rule says that do use your mutex and data together. For instance, you can use synchronized value. And it's not in the standard, but you can implement it your way. There are some limitations right now. It's only available in GCC 13 and onwards. And it's an experimental implementation. You won't have it in your Clang, whatever version. I checked latest like a couple of days ago. It wasn't available. So only C++, and it's heavily limited. It only works with mutex. Can be easily extended to whatever lookable, but right now it's only mutex. That's how it is proposed in the paper. And it doesn't work with context. So in const methods, you cannot use it at all, which is a bummer, which I believe should be improved before it gets standardized. And it doesn't support shared locking. So if you have a shared mutex, you cannot shared lock it or exclusive lock it. You always exclusive lock it. So that's that's a corner case. I mean, okay, for some situations, it may be important to have exclusive versus shared locking. And it doesn't work with condition variables in any way, which, okay, one can argue that, okay, it's not for that. Oh, sorry. So I obviously wasn't happy with the current state of affairs, so I went as far as implementing this proposal my own way. You can check it up on GitHub, and I tried to improve all these deficiencies that I spotted. Whether I succeeded, you can judge, and the community can judge. But I made it possible to use whatever lockables and work in const methods. And experimental support for shared locking as well. So coming back to our pyramid, we've got synchronized value, the subject of our talk today. And this goes to demo number 3, and it will be the last one, I promise. So at demo number 3, synchronized value. I mean, that's pretty much everything you've already seen on the slide. We've got some financial data. We've got some ownership data for our account, and we've got money. Maybe let me make it a bit larger. And these are protected by distinct mutexes. And we've got this add amount thingy. Look at this helper method. It takes financial data as a reference. So we are absolutely sure that this financial data has already been logged. No questions about it. So we can simply assign the new value to that. No worries. So that's the thingy. And yes, I said that original version, the GCC version doesn't work with const. So let me remove this beautiful macro over here, and let me make the console a bit larger, and let me rebuild it. And what? Oh, I forgot this TSAs. Okay, sorry. No, I should have disabled it before. Will it work now? Yes, it does. So there we go. Let me rerun it because, okay, this previous example is taken care of. If we remove this condition here, and we actually try to use apply with a synchronized value in a const method, it doesn't work. It says something like, where is it? Incompatible CV qualifiers. And that's because const synchronized value of t is not the same thing as synchronized value of const t. And that's a subtle detail that needs to be, in my eyes, needs to be added to the paper in order to be able to use it like so, because like it's an important use case. In the current shape, it doesn't really work production-wise. So that's roughly it. Yes, that's the synchronized value. Let me proceed to the summary. The feature matrix. I mean, we've come a long way. I don't expect you to read it. Please don't. My point here is like support for certain things, certain capabilities varies across both standards and libraries, and maybe some custom implementations or custom things. There are alternatives. It's not like the synchronized value is the only option. I already mentioned there is boost synchronized value. It's another implementation that works slightly differently. There is libguarded from codebase, the company, and they implemented something similar, but it doesn't work with multiple mutexes. It only supports a single one. So it's somewhat constrained. There's Facebook Folly. If you are into Facebook ecosystem, it's a massive library with many utilities, and it's multi-featured. You can access it with the Lambda way and the handle way, which I showed, I mean, the handle / proxy object manner, which I showed that in my eyes is somewhat dangerous, but maybe user wants to use it. Yeah. So it's available in Folly. And I used to say previously when I gave this talk that there is Google AppSale with the AppSale Mutex, but it's, I mean, it does exist, but it doesn't do the thing that I'm discussing. I checked it again, I stand corrected. It's a custom implementation of a Mutex, which can do a lot of things for you. It's compatible with conditional variables. It can detect deadlock at runtime, and it truly does the full search of the graph, so it tries to detect a cycle in a graph. And if you happen to use only those mutexes, you're on the safe side. But otherwise, I mean, in a mixed environment, not really. Yes, but it exists. You can check it up. It's a different thing, essentially. So coming back to our pyramid to fill the top, there is still room for improvements. It's not a solved case. And who knows what future brings. And if you like Valgrind, one final note. Valgrind is completely blind to certain scenarios involving conditional variables. If you haven't known it, I haven't. I've read the manual. It's fabulous. I highly recommend that you do the same. Thank you all. If you care to give me some feedback, here's the QR code. You can scan it. The links to the materials will be there as well. And I'm happy to take a couple of questions.
Very good presentation, Bartosz. Thank you very much.
Thank you.
I have one question. Basically, what's your take on the potential problems with synchronized values? I mean, like, it will be now very tempting to create, for example, synchronized value of, I don't know, customer, containing some personal info, maybe balance. So these data could be potentially modified independently, but now will be bound to a single mutex, creating, higher contention. So
I believe it was addressed in the code that I showed, where you can split the data which can be accessed independently and have two synchronized values. And if you are in a scenario where you need both of them to be modified, then you simply log both of them in a deadlock avoidance manner. Otherwise, I mean, you can chop it into however many pieces you want if it serves the purpose of your application.
Right. So yeah, that's basically my question, because we would, to have it like most efficient, we'll be still dividing and creating an association between a mutex and a piece of data that it protects, right?
Yes, we will be. And I mean, it doesn't change anything compared to our today's standards. If we want to access a subset of data safely and split it from the other subset of data, maybe distinct, we still need two mutexes. If we think we don't, then either we log too much or we have an error in our program. So in my eyes, it doesn't change anything. It just makes you forcibly use mutex wherever it belongs. That's my take.
Makes sense. Makes sense. Sure. Thank you very much.
Okay, we have a question there.
Sorry, I can't see with the light into my eyes. So, over there at the top. Yes.
Hi, thanks for the talk. I wanted to ask about the, is there like any efforts ongoing for standardizing the usage of condition variables with synchronized values? Because like in my head, this is like one of the key use cases, because for multithreading, you need to have a communication in between threads, and this is basically where CV kicks in. So like without it, it would be like 50% bake, I would say.
I sort of agree. Yes, I mean there are cases when you don't need CVs, but there are cases where you absolutely need them, and period. And right now there isn't any support. And I actually, when implementing my own variant, I was like giving it a thought. I didn't quite succeed. I mean, let alone to implement it. I would be bragging about it otherwise. But I didn't come up with any good solution so far architecturally how to like marry the two together. I have some ideas, but it's so. So if you happen to have any, I would be more than welcome to talk later.
Yep. Okay. Thanks.
Okay. Hi. I would want to ask about STD atomic. What's your opinion about it?
Hang on, I'm afraid I can't see where you are. So. Right. Over there. Hello. Right, Stud Atomic. What about it?
Because it seems like it somehow functions in the similar way, like it can fulfill the similar role.
Yes, so long as your synchronized data type is the size of this atomic. And atomics are implemented in such a way that if there's an underlying hardware support on your CPU for certain data types, say an int, 32-bit or 64 if you're on 64-bit architecture. There are hardware instructions to compare and swap in the hardware as a single instruction, and that's where std_atomic is reasonably used. Otherwise, every single other std_atomic has to be necessarily implemented with a mutex. So with certain specializations of std_atomic, the ones that have underlying hardware support, yes, you get the benefit of a single processor instructions. Otherwise, it's like, oh dear, I mean, we need to use some other primitives.
Okay, thank you.
By the way, on std_atomics, let me just finish the thought. Std_atomics, not in the sense of C++, but atomics in the sense of like more generically, these are used in Linux Mutex syscall. So the Mutex stands for fast user space mutex, and it works in such a way that it will try to optimistically compare, modify, write an atomic. And if it fails, then only then it goes back to the kernel and says, hey, okay, I have failed. I mean, I need your help here. But if it succeeds, like you don't even get the context switch for going into kernel. That's a nice one. I believe there was a question. Yes.
But we have also Mike there, and I think someone was waiting, correct?
Okay.
Yeah, so let's take that one first.
Over here,
All
right?
right. Hi. So this synchronized value, how does it work with coroutines? Like if you suspend a coroutine in your apply function, then you essentially leak the pointer, right? And when you await it later, and it resumes the execution.
I'm not familiar with coroutines to that extent. However, I suspect it's like irrelevant to coroutines because you just well, do you do any regular mutex locks inside a coroutine, and can you do it? And I admit I'm not qualified to answer these questions.
You better not.
Sorry?
You better not.
You better not. In the sense, okay, it wouldn't be compatible if you shouldn't do that.
Thank you.
Okay, thanks for great lecture. I have a question about because the world of the programming, they have several other approach to the problem of trying to run something parallel. For example, Node.js do not use the threads. There are single threads services, and in C++ we are still using the multithreading. It's okay because it's much more efficient than creating separate process for trying to parallel something. But don't you think that the problem with multithreading in C++ is that we are trying to do code most efficiently, and then we are making complicated synchronization structures with using, as you shown, with several mutexes. And the second is that we still don't have the great tools for testing multi-thread code. Yes, what do you think? How we can test multi-thread code in unit tests? And don't you think that it is very uncomfortable in tests?
So let me summarize. The claim here is that like single-threaded applications are way easier, and we don't need to take care of all these bits and pieces. Yes, that's true. The flip side is you only get to utilize a single core. And in a multi-core systems, which every one of us has in our pockets today, in the form of a cell phone, they come with 2-core, 4-core, 8-core, whatever, 2 processor something. It's like the choice, do you want to utilize all the other n+1 cores? I mean, 2 towards n, except for the first one. So if the answer is yes, then you'll probably end up in a shared data situation where you absolutely have to synchronize. So that's one thing. You can copy the data, as I mentioned in the beginning of my talk. If you can afford copying the data such that every thread has its own copy and never accesses the other thread's data, you don't need to synchronize at all. That's fine. And what was the last?
About the
testing.
approach to testing, yes,
Yeah.
because we still don't have the great tools, yes, to catch every.
Yes, no, well, it's a tough subject. It's not like we don't have anything. Valgrind is fantastic, except for this one thing that I showed in the end, which was a surprise to me myself. So yes, Valgrind is good. It will catch everything. Sometimes you cannot afford the cost of running something in Valgrind because the cost is like 20 times the time and however much time, like at least 10 times more the memory. So it may or may not be feasible in your case. I admit, I mean, it's difficult. It's a subtle subject, and does it take better tooling? Whatever works, yes.
Okay, thanks.
Okay, we are coming to the end of the time, so maybe last question, and we are closing, okay?
There's one.
The last one.
Great presentation, thanks. To build up on that atomic question, do you think it would be beneficial to turn synchronized value into sort of a Swiss Army knife and have a specialization for smaller types to basically use atomic underneath there, since you don't need a mutex for smaller sized types that can be turned atomic? Or should it be kept simple and just be a means to tie a mutex to data and not do anything fancy, just...
So given that there is this callback style, and you always pass the callback within which you get to do whatever you please with the data being logged, I don't think that the two approaches can be combined anyhow. However, since you think you say that I modify some atomic, yes, so long as you know upfront what you want to write into that atomic, then you can utilize concurrent swap or whatever it's called on your system. And in this sense, you don't need to create a mutex in the first place. And by extension, you don't need to create a synchronized value which has the mutex and the data. You just create the atomic data, assuming that this data actually does support atomic operations in hardware, because that's important.
Okay, thanks.
Okay, big applause for Bartosz. Thank you very much.
Thank you.